really want to take his cool off,
Boy, throw it.
I just press this early in the morning, when she on my mind. I'ma take my time, yeah. Do it how we want, just to set the mood. Girl, I brought some modern day and Chardonnay.
Alright, so the Higgs boson, or the God particle. I like the God particle. It's a good name. Maybe because it has God in it. Also because I have God in my name. Oh well. In any case, right, the Higgs boson is a boson, which, in case you don't know, is a subatomic particle. Sort of like a force carrier. Extremely similar to a force carrier. In fact, some force carriers are bosons. It's like that rectangle square dilemma that some people have. In any case, yeah, so boson's important because it fills a giant gap inside the standard model, which is basically all of quantum physics summed up in a model. Alright, so the Higgs part of it. Yeah, the Higgs boson is a sort of representative of the Higgs field. And the Higgs field gives things mass, like photons. In fact, photons don't have any mass because they don't interact with the field, so they just zip on by. Yep, and that's how we have mass, people. Very disappointing how it's just not really all that rooted with you. It's more like just a giant field of stuff. But in any case, yeah. That's how we get mass and madness and all this other good stuff. In any case, right, so when they were finding this out, they couldn't exactly, well, when they were theorizing that, they couldn't exactly make it, and they still can't really make it. Well, okay, they can make it, but they can't, like, observe it. They can just, like, see the after effects of it because it's like it decays in, like, a trillionth of a second. It's really, really fast, so no one can really just observe something like that. But we can get the aftershocks. The after waves, the after effects. Yeah, that's good. In any case, yeah, so we can see those, and by that we've also theorized that it's definitely possible to exist, and that it does exist. Yeah. We also did during the Large Hadron Collider, which is a particle accelerator, in case you don't know what that is. Yeah, good stuff. Great stuff. I'm not too good at explaining this stuff, so I'll just have someone else do it for me. Here we go. I guess I'll let you guys listen to this video.
If you've had any interest in physics at all, you've heard about a thing called the Higgs boson. But just what is it, and why is it interesting? In 1964, a physicist by the name of Peter Higgs took some ideas that were floating around at the time, added an insight or two of his own, and proposed that there was an energy field that permeated the entire universe. This energy field is now called the Higgs field. The reason he proposed this field was that nobody understood why some subatomic particles had a great deal of mass, while others had little and some had none at all. The energy field that Higgs proposed would interact with the subatomic particles and give them their mass. Very massive particles would interact a lot with the field, while massless particles wouldn't interact at all. To better understand the idea, we can use the analogy of water and swimmers. In our analogy, the water serves the role of the Higgs field. A barracuda, being supremely streamlined, interacts only slightly with the field and can move through it very easily. The barracuda would then be similar to a low-mass particle. In contrast, my buddy Eddie, no stranger to donuts, can only move very slowly through the water. In our analogy, Eddie is a massive particle made massive by interacting a lot with the water. The lightest of the familiar subatomic particles is the electron, while in the subatomic world, the king of mass is the top quark. It weighs about as much as an entire atom of gold, about 350,000 times more than the electron. I'd like to stress that we believe the top quark is not more massive because it's bigger. It's not. In fact, we believe that both the top quark and the electron are exactly the same size. Indeed, they both have zero size. The top quark is more massive than the electron simply because it interacts more with the Higgs field. Actually, if the Higgs field didn't exist, neither of these particles would have any mass at all. Now, in the press, you don't hear about the Higgs field, but rather the Higgs boson. How are these two things related? The Higgs boson is the smallest bit of the Higgs field. To understand how that works, we should again return to water. Everyone knows what water is. If you're immersed in it, you know that water is everywhere. It's a continuous medium, and there are no holes in it. We also know that water is made of molecules, specifically H2O. If you hold these two ideas in your head with the realization that water consists of countless individual molecules, you can now begin to appreciate the Higgs boson. The Higgs field that gives subatomic particles their mass is made of countless individual Higgs bosons, just like water is made of individual molecules. You should keep in mind that the Higgs boson hasn't been discovered yet, and what I'm describing is simply the most popular idea as to why subatomic particles have the masses that they do. As I speak, my colleagues and I are studying data taken at huge particle accelerators to see if this idea is true. Stay tuned.
Pay attention to the slower people.
If I could save time in a bottle, the first thing that I'd like to do is to save every day till eternity passes away, just to spend them with you. If I could make days last forever, if words could make wishes come true, I'd save every day like a treasure, and then again I would spend them with you. But there never seems to be enough time to do the things you want to do once you find them. I've looked around enough to know that you're the one I want to go through time with.
So, why did I just show you guys some good old-fashioned high-speed action? It's because accelerations, man. Accelerations. That is the whole point of the Higgs boson. Well, it's majorly the point, mostly the point, probably the point. In any case, yeah, so the particle accelerator is how we found it out in the first place, and it just kind of collides everything together. When you move close to the speed of light, yeah, stuff starts to get a bit wonky, and that's kind of how we found it. But in any case, with that whole founding thing, we complete the standard model, and as far as I can tell, the standard model seems to really kind of just tell us everything we might want to know about the universe. Not everything. I mean, it just about everything we might want to know about the smallest portion of the universe. Because I mean, we don't even we can't even see 96% of it. So with the dark matter, dark energy thing. So I mean, cut him some slack. But in any case, yeah. So with that, the theories flow in. One such theory is how the Higgs boson got the name God particle. In other words, I believe it caused like the major changes during the Big Bang. I mean, it does control mass, so you can see how that could work out. It when it happened, everything was basically energy, and then it kind of just gave turned the matter into mass. The energy field turned it all into mass and stuff like that, which is sort of why E = mc². Like mass and energy are practically the same thing because the Higgs field is an energy field, but it also gives mass. Yeah, so there you go with that. But in any case, yeah, so right on that point, the Higgs boson should be able to help us out with a very, very important detail in practically all of science, which is the theory of quantum gravity. And if you don't understand how that could help out with it, think of it like this. In physics, half of the equation that involves with gravity involves mass. The other half is with the distance, and I mean that's honestly not even as big a point as mass is. So if we can study mass in such a detail that we have the Higgs boson, I mean it should be easy to figure out how gravity works to almost the same level of detail. And with that, once we figured out the theory of quantum gravity, quantum mechanics and general relativity have finally meshed together, and Einstein's dream is complete. Whoop-de-doo, man, we're going somewhere with this. Plus, there's also the completion of the Standard Model, which doesn't really tell us too much about all of the giant cosmic madness that just happens in outer space, but it does tell us about some really interesting stuff, like quarks, neutrinos, all the basic stuff, like light and all that good stuff. I mean, like, we are trying to figure out how to teleport here, guys, so being able to understand these basic particles should really help with that. I do realize this is all theory, so should we just ignore this like it's not even happening? Yes, no, maybe, nah. Anyways, back on topic. Now that we know the Higgs field exists, somebody somewhere is definitely going to make some kind of machine, some kind of a sensor, so that we can see mass of an object just by looking at it, and that'll majorly help out, especially with astronomers, especially when they look up at the sky and they see a giant black void, especially when that giant black void is blocking out a bunch of our view, and you can see stuff orbiting around it, but you can't see it directly. Oh, so much curiosity, right? By the way, I'm talking about dark matter. So the Higgs boson may not warrant the name God particle, but still, that thing's going to be useful in the future. It's already been retconning a bunch of old theories that we found out are wrong. So I mean, hey, you never know. Maybe we'll just figure out how to do time travel with it. Stay tuned, man. Pay attention to the news. It may just come up that we just so happen to learn how to do stuff and you guys get left behind. Pay attention.